We implemented the temperature converter as an algebraic equation in Simulink. Now let's implement the same function by using a lookup table. Add a lookup table, double-click on it, and add the breakpoints for the input temperature in centigrade, -60 and 100. We use square brackets as it is a MATLAB vector. And the breakpoints will map to the table values in Fahrenheit, -76 and 212. We also see that the block graphics changed accordingly. For testing, we need an extra interface port. I go to EverTest interface sheet, copy the line, and add a capital L for lookup. As you see in the test case, the output is missing here, so I use the cleanup button to add it automatically. Click on the EverTest update. It adds an extra port for the EverTest sync block. Connect the signal and run the test case. It seems that the output values are not exactly as expected. So let's copy the reference values, clean up, and run the test case again. With the lookup table, we are pretty close to the values that we received with the algebraic equation. But the results are a little different as the lookup table block is using a linear Lagrange interpolation to calculate the outputs. Different algorithms provide different results. You can play with the lookup block settings to see how it influences the outcomes. The chance is that we can accept some signal deviations within a tolerance band. So I open the EverTest settings and define a small number as a global tolerance, 1 × 10 to the power of -5. Now we see that the values, which are not exactly the same, are colored in yellow to indicate that they are not exactly as expected, but are still within the tolerance band. Another way of validating our algebraic function is to compare the outputs with those from the lookup table in Simulink and to provide the difference values to the EverTest sync. It should be close to 0. We subtract the values, introduce an extra port for EverTest sync, clean up, and run the test case. We can see the signal deviations, and we can see that they are very, very small. This approach does not require to define the exact reference values. It is referred to as metamorphic testing because we are now proving the metamorphic relationship between the output and the input by knowing how this kind of a system should work. I can even simplify this test case and remove the direct comparison. Clean up. We see the signal flow in the debugger. The difference is 0. Now we have a very small difference. 0 again. I hope you get the point.